All right, everything that is said between now and the last talk will be recorded and it'll be available online. So I'm just gonna go into the talk here. Okay. So, with no further ado, today's talk is called Genie. So it's about generative interactive environments, which is how they frame what a world model is. We'll get into that more later. There's a cool little lamp there. If anyone wants to rub it, they can have their wishes granted. You know, just be careful what you wish for. You might get it. So this is the paper. So actually, I don't think I left it up the last time. So if you want to get the paper on your phone so you can follow along, you can scan that QR code. I will have screenshots throughout the talk, but having the paper definitely helps, especially if you want to like zoom into some of the formulas or anything. Okay, all good? I think we have one more person. Yep, go for it. All right, thanks. Okay. So I want to talk about some stuff before we get into this world model stuff. We talk about LLMs a lot, which means large language models, but there's also a thing called a language model. And I'm not talking about small language models, it's like another thing. You know, we have, you know, when ChatGPT came out in 2022, there was a lot of work that went ahead of that enabled that breakthrough as a product. And everyone's like, oh, it was transformers, and that's definitely true. However, there was another thing that was probably just as important, if not more, which is next token prediction. And if you look at, you know, these are not drawn to scale because ChatGPT generated it, but if you look at the top left one, that's how much data that BERT was trained on. And BERT is it's a form of a language model. It's generating these embeddings, and it's also based on transformers. But you know, scaling it out doesn't give you the same benefits as something like GPT. And the reason why is that GPT was trained, it was pre-trained to be more precise, on doing next token prediction. Why does that matter? Like, this is not a small thing. Next token prediction lets you take arbitrary data off the internet without labeling it and then train a model on it. And for the longest time, that was like, you know, that was like really difficult to conceive. Like, how would you train a model without labeling data? You know, supervised training. And once they figured out, hey, just try to predict the next token in the sentence, then this created this huge unlock. And you can see the amount of data that's labeled that we can use is significantly smaller. It's probably less than 1% of the data that is unlabeled that's out there. And you've probably also seen these like text-to-image models. So if you're doing like the Ghibli stuff, you know, that's generating images, you can ask a lot of models now to generate a photo for you. And now with Sora and, you know, Hunyan Video and WAN and a few other models that have come out this year, you can do text-to-video generation. But this is still, you know, kind of similar. We're just giving it a prompt, we're getting an output. And what a world model does is quite different. But you might have maybe had experience with, my apologies, you might have had experience using an agent. Has anyone here used like the agent mode in ChatGPT? Okay. And so agents can kind of struggle. Like I asked it to like scrape some websites for me because I was doing something totally, you know, okay. And it just like crapped out after a few instances and it just wouldn't budge. A lot of agents can be pretty unreliable. And that's because with agents, we're actually asking them to do something a little different than generating photos or videos or text. We're actually asking them to understand the action space and the environment and how actions lead to changes in the environment. Like if I pick up this laptop and throw it at the wall, I'll be out of $1,000. The model needs to understand what consequences there are to an action. And that's not always evident right now. So an example of this is, I gave a talk earlier this year in May on Gemini robotics, and I'm gonna show you a video here really quick. And then we're gonna come back to this. Okay, the audio's not porting over, but.
Can you put bananas in the clear container? Can you put the grapes in the clear container?
It's in box.
You're just talking to it. It's not code that he's writing. He's just talking to it as a microphone.
Can you put the grapes in the pink container?
Okay. Looks impressive, but it's not. Here's why. Okay, he didn't like that. Yeah. Okay. So the green column is representative of what he showed you. So 96% of the time, it's able to do what you just saw correctly. The red column, the fruit bowl, it's only able to do 4% of the time. And if you notice, he stopped after 2 types of fruit. You know why? Because the fruit bowl experiment requires him to put 3 fruits. So the moment you say put a banana, a plum, and an orange in order sequentially into the same bowl, it only gets it right 4% of the time. So it went from 96 to 4, right? So, and they spent, so Gemini is nothing small. It's like a big project initiative inside of Google, and they work really closely with DeepMind. So they're some of the brightest people in the world, and they're getting 4%. And what's the issue here is not that different from where language models were before we had next token prediction, in that it took them a whole year to train the robot and label all the data to do what you just saw. Like they had a whole team spending a whole year just on collecting data, right? And they're still getting abysmal results when you have any slightly higher level of complexity than just 1 or 2 fruits. And so we need to find a way to train, I'm putting agents and robots as one here, and in the sense that they're both autonomous. Like we want them to act on their own, make decisions, understand how the environment is affected by their actions, and so forth. And so in that sense, they're very similar. And when you solve one, I think solving the other gets a lot easier as well. And we have to find a way to do self-supervised or unsupervised training of agentic and robotic systems. And that's what Genie is actually about. So if you look at what Genie does, they only take video input for training. This is not too different from taking just unlabeled text to train an LLM. And they don't need actions like the other world models need, and they don't need text. They literally just need video, and I'll show you how that works here later. This is really important. And just to clarify what a world model is, a world model isn't just generating a picture or a video or a text. It's actually rendering a game engine using a neural network, right? And so you'll see here, you can take a photo, give that to the Genie world model, and you can start playing a game from that photo. So you could take like a screenshot of a Mario game, or you could draw, like hand sketch a game that doesn't even exist, and it'll render out the future gameplay as you control it with a controller. It's not live, it's like 1 FPS right now, but this is showing a lot of promise. So the core idea is we want to actually map actions to the environment, and we want to get those actions just purely from video without labels. Because the Gemini team spent a year, right, just labeling. So what Genie enables is users can act in generative environments without needing any labels, and we can just do this with a large corpus of internet videos. I don't think the gap between YouTube and DeepMind would be small, large, so this really plays in nicely here. So Genie is not one model, it's actually 3 different models, and they collectively add up to just a few billion parameters, and we'll get into that. There is a video tokenizer. This is probably the simplest one out of all of these 3. So is everyone here familiar with like tokenizers in general? Like how they're used in language models? Okay, so tokenizer is taking text or pictures or whatever, and it's breaking it up into chunks called tokens, and then it can represent that, and then that's used later on. So you're not using direct like characters or full words, you're using tokens or patches of an image. So that's all the video tokenizer is doing. And then there's a latent action model. And what the action model is doing is it's learning what the action was between a bunch of frames and then the next frame. So if in the video I'm still for a few frames and then all of a sudden I've moved, the action was that I walked, right? So that's what that's doing. It's just learning the action space, but it's not learning it as labels. It's not saying, oh, he walked, or oh, he jumped, or he steps backwards, or whatever. These are all latent, so they're all vector representations that don't have semantic meaning just yet. And we'll show you how that gets mapped later on. And then there's a dynamics model. That's the last part. And the dynamics model takes as input the video frames, and it tries to predict the next frame. So it's kind of like next token prediction, except it's also getting action. So now we're explicitly modeling action instead of just environment, right? And this is the breakthrough here, yes?
And so action could be like, WASD or something
Yeah,
like that.
exactly, yeah. It could be clicking, it could be certain keys on your keyboard. So I'll show you how that maps out in a moment, but that's exactly right. And in the case of Genie, they only have, I think, 8 actions. So these are the 3 main components, and we're just gonna deep dive into these. And keep asking questions if anything's not clear. So what the video tokenizer is doing is just, it's a variational autoencoder, but it's not just any autoencoder. So let's start from the top, which is actually the rightmost part of that acronym, the AE. An autoencoder takes as input data, and then it produces the same data as the output. Sounds useless, but it's actually very useful, because in the process, it has to compress it into a smaller representation space, and then uncompress it. That's called decoding, back into the same space. And in that process, it learns to ignore noise and find the signal. So it's like if someone gave you a picture and they deleted a giant chunk of it, and then you ran it through the autoencoder to actually reproduce the patch that was removed, because it can understand contextually around it what should go there, as an example. So the video tokenizer is taking the video input. They use this term called ST transformer. That means it's spatiotemporal, so it's looking at height and width of an image. Also temporal, time, which is just frames over time. And the VQ means vector quantized. So it's interesting. A VQ means that there's only a fixed number of representation encodings you can have. So it's not a continuous space, it's a discrete space. And that makes it a lot easier to train, because you're just trying to put it in a box instead of trying to find the exact continuous value. In the context of the action model, they also have a VQ effect, and that's how they have 8 action spaces, because they only have 8 codes that can be represented in the VQ VAE. So the way it works is we take in T frames of the video, which is marked as X1 through T. So these are just like frame 1, frame 2, frame 3, etc. And then it generates these discrete representations, and then when it decodes it, you get back to the X, right? But we actually care about the discrete representations, and that's what's used later on. So that's from the bottleneck layer from the embeddings. Then the second component is the LAM, the latent action model. And what this does is it learns an action based off of the previous frames up until the present, and then the next frame. This is only done during training, right? Because in inference, we don't know what the next frame is. We're predicting the next frame. But during training, we have this corpus of data. And so we do know what the next frame is, just like when you're training or pre-training a language model, you do know what the next token is. So you can compute the loss, and you can train the model. And this is like a big core breakthrough in how they're able to map the action space. So yeah, it just takes the input from the previous ones, and then the next one, and then the output of the LAM is the action, okay? So there's only 8 of these in this model. And then lastly, and I believe this is the largest model out of all 3, this is the dynamics model. This takes in the video tokens and the action embeddings, and then it predicts the next frame, okay? So going back to the full thing, that's how it looks together, okay? Any questions so far? All right. Yes?
So I've seen stuff where they're doing non-real-time video games with this. Are they actually taking user inputs as part of training and turning that into vector space for actions that then?
That's a good question. So they're taking user inputs during inference. In training, they're not, because taking user inputs during training would basically be labeling the data, and they're trying to not label the data. So during inference, they actually throw away this. They actually throw this away. So I'll show you how that works. But so during inference, during training, they're learning the action space from just raw video. So like these frames versus the next frame. That's it. And then it's inferring, oh, what was the action taken? Did the person jump? Did they run? Did they stay still? Did they use a weapon? Did they use a shield, etc.? Yes.
The extract plus one is generated with the video model.
That's from the training data, I believe. Oh, you're talking about x of t plus one, or are you talking about x of t x hat, or are you talking about x?
This had one, so it's
The hat. Okay.
It's not the same input as output, so there is a difference.
Well, yeah. This is so you can compute the error, so you can actually train the model. So it's producing the x hat prediction, and then you can compare it against x t plus one as a ground truth. And it's the difference between those two that gives you the gradient. Yep. Okay. Yes. Yeah, we'll get to that. Right now, it's not. So during training, this is latent actions. So these are just 8 vectors. We don't know what they are just yet. Okay. Okay. So this is the model size. The total model size, they say it's 11 billion. It's actually 10.7. And almost all of that goes in the dynamics model, right? So 10.1 billion goes in the dynamics model, and then we have a few hundred million parameters each for the LAM and then the video tokenizer. And it was trained on 942 billion tokens. So same thing, 200 million for the video tokenizer. Patch size is 16, so there's like a bunch of specifics. And then the sequence is always 16 frames, and then they're running at a 10 FPS. This is during, I guess, training, or they're sampling 10 frames for every second. Maybe the actual game is like 24 or 30 FPS or 60, but they're just sampling like 10, right? When they're actually playing the game from the Genie model, it's only 1 FPS, so it's pretty slow. And then they trained it on 6.8 million 16-second clips, which is 30,000 hours of video. So I don't know how much, how many hours the Genie team put together, but they're gonna rip through this a lot faster because this is self-supervised. They took the data set they just got video footage of platformer games. Does anyone here know what platformers is? Okay, what is platformers?
Basically, you take your Mario or whatever character, you jump, go left, right.
Great. Great. Okay. So platformers is what they trained on, and later you're going to see they did an eval on a completely different data set. So they did a lot of out-of-distribution stuff. Yes.
I was just going to say, you maybe we're going to touch on this, but in the appendix they talk about this data set, and they originally started with a data set that's 10 times the size, and they have an interesting filtering paradigm where they come in and train a labeler to label with quality.
Yes, you're right. It says 55 million, and then it went down to 6.8. Yeah.
Yeah, I think it's really interesting in this paper is that the action models like themselves don't get this.
That is interesting. Yeah, I didn't think about that.
Yeah, I'm like token prediction, just to see how things go.
Right. Yeah, you're not seeing the past. That's a good point. I wonder why they did that. I wonder if it was intentional.
I thought it goes into here that they had to stop gradient action on the latent action because it's like one of these things that you accumulate all the gradients that they're just gonna flow into each other. You don't want it to
Okay.
start memorizing like when you do this thing because you did that action.
Okay. So AI slop is okay when they push content, but not when they're training gradients. Okay. Good. Yeah, so there's basically 2 phases during training. So they only train the video tokenizer so you can have a good understanding of how videos work over time as well. And then they train the dynamics and LAM at the same time. During inference, we actually take the LAM, the action model, and we throw it away. Why? Because we now have these 8, they picked 8, but you can pick whatever number you want. You have these 8 actions and they're unlabeled. Now I'm going to give you a really hard quiz. What is easier to label? 30,000 hours of footage or 8 actions? That's the breakthrough, right? You're only labeling these 8 actions. So you say, I'm going to activate the first code out of the 8, and then I'm going to see what the character does in the game. Okay, and now I know the first one is to stay still. Now I know the second one is to run. Now I know the third one is to jump, whatever, right? So you just do that 8 times, and then you're done, and you can throw it away. And then now you're just feeding that. So if there's some software program, it would take the user's remote or controller or keyboard, and it would map it to one of those 8 accordingly. Yes?
Do you need to actually go through and label the data, or at least from my understanding of reinforcement learning, you've got the gameplay here. I choose random actions, and it changes the state of the screen, and I can I start to learn how it changes the state of the screen, and then I can apply that to a new random frame when given that action.
I'm not sure I follow. Are you saying to do random actions to get what exactly?
I'm saying, why do you need labeling for the gameplay itself?
Oh.
When
Oh, just for it's just for the user's convenience, because they might, if they're using the WASD, they might be used to certain keys mapping to certain actions in the game. Because otherwise, it would be every time you retrain the model, you'd have random configurations of which keys map to which actions.
Okay.
So it's just for the user's convenience.
Okay.
Yeah, I think to answer your question, in general, yes, in RL you need it, but in this case, they actually just teacher force it.
They just do what? You said
They just teacher force it. Like you would
One more time?
see-
What was the word?
Teacher forcing essentially means you give the model as labeled what will the next thing.
Teacher forcing, you said?
Yeah, it's called
teacher forcing. Okay.
So it's like if you're doing like next token prediction,
Mhm.
like in training, you get the next token as if it was correct.
Right.
So in this case, like as the model gets trained in the pass slot, or in this case, in training the dynamics model, you show them like, okay, here's a frame, and then you push like a key. Now here would you predict the next frame.
Okay.
But in training, that next frame is already passed in as if you got it correct.
Sure.
So that's kind of like why you don't see this RL loop. It's like, it's already in that dynamics model of saying, okay, in this frame, here's your frame. If you were to say, I push this button and there's this character, what the model then does is saying, okay, like you would jump up. So let's showcase up.
Okay.
Next frame, the character's already in the air.
Okay.
But what would you then do? So it's kind of why they don't have an RL loop here, because they've already given that information.
Thank you.
Cool. Yeah, so when we're actually playing the game, this is when we're doing Genie inference. So x of 1 is the first frame. So this would be like, if you like hand sketched a drawing of a scene that you want to play in with a character, you'd give it x1, then the tokenizer, the video tokenizer would produce the embedded representation z1, and then also the actions the user's taking. So which key are they pressing? If any, that goes to the dynamics model, and then it predicts the next frame. So it's actually doing it at a frame by frame level prediction instead of chunks of frames. It was sampled at a lower FPS, but still. So this is what it looks like. You can take a hand-drawn sketch, which is the pink one. You can take a real-world photo and just play it out in the real world, but it's not real. It's a Genie. And then you have the text-to-image, right? So it doesn't matter what the input is, it's able to generalize. It generalizes so well that they explicitly did a lot of their evals on outer distribution tasks. They took another data set. This is in my appendix. So I'm at 26. So they took another data set. They call it the robots data set, or RT1. And this is what they did all the evals on. So if you want to figure out what that is, you can look at that. And you can see here that they're able to get it to do the same thing even though it's starting at a different point. So what you want to look at is the prompt, the left column, that's just the input, okay? And then each of the 3 columns after that are different actions, down, up, left. And I want you to look at where the robot's hand is. It doesn't matter where the hand starts. When they press down, it goes down, right? So from here, I know it's not easy to see, but on the top left, you can see the robot arm is up in the right, and then when they press down, the robot's arm goes down. And then in the second row, the robot's arm starts at a different position, and then in the second column, you can see it's moved down. It didn't move down a lot, but it did technically move down. But that's true for all of these cases. So it's able to generalize, even though it was not trained on this. It learned parallax. So the dynamics model it understands parallax innately just by learning from the footage. Parallax is like when you're in a car, and especially if you're a passenger, don't do this when you're a driver, but if you're a passenger in a car, you stare out the window and you look, the objects that are farther away seem to be moving slower, the objects that are closer to you seem to be moving faster, right? So that's what that is, and that's true for all the games in the training data set, so it learned that in the dynamics model. And then the other thing I want to talk about is like metrics, like how do they measure if it's working or not? So there's 2 types of metrics they care about. There's a video quality, and then there's like adherence to the actions, right? So for video quality, they're using FVD for Shea video distance. It's related to FID for Shea inception distance. This is just a way to see how like realistic or good videos or images look as rated by humans. it's a bit of a problematic metric, but it does seem to work well enough for them. And then for controllability, which is like how often does it actually like listen to the action properly, they modified PSNR. So PSNR is like a common metric that's used oftentimes for evaluating like image quality, and they're using it in a really interesting way. So they're saying like, do we have like, so PSNR means peak signal to noise ratio, right? So you want that to go up. So a high PSNR is a good thing, and a low FVD is a good thing, right? And to see if it works, what they do is they compare it to random actions taken as a baseline, and then they compare that against when the actions are being taken according to what the user's providing. And as long as that delta is big enough, then they know it's controllable. This allows them to measure that at scale. And we can see that the FVD and the PSNR are better here. What's weird is that if you look at, for the robotics data set, so if it was trained on platformers, and what's funny is Genie actually did a little worse, all right, in this case. But it did better in both of these cases for robotics, and it wasn't trained on the robotics data set. So that's very, very interesting that it didn't just do OOD, it like broke through that hurdle really well. I think this has like really, really broad implications for the industry. So it took about like 5 years since Transformers came out in 2017 for us to see something like ChatGPT. Obviously, there was a lot of work that went into in the AI industry before Transformers came out. Like next token prediction has been actually run for a few decades. But all these things came together and they coalesced and they gave us like a real product, ChatGPT. If you look at the timing of that, 5 years, it seems like a lot when you hear like projections these days about where AI is headed. I think it's still a pretty reasonable time frame. So I'm expecting that if Genie came out, last year, we could probably see the fact that we're able to do self-supervised training of an action space for agents and robots. We should see some kind of like a ChatGPT moment for agents and robots well before 2029. I think it will be accelerated, but that's just kind of where I'm at here. Thank you. All right, the next talk is going to be from Ben Sander. So welcome aboard. Okay.
Let's go. All right. Howdy. You guys can hear me, I assume? Does that sound good? So let me just introduce myself. So I'm Ben. I've worked at AMD for 30 years. It's even worse than I actually interned at AMD before I started my 30-year term. And so what I work on is AI software and performance and architecture. So that's what I'm mostly going to talk about today. A little bit different than some of the other talks. Actually, one of the reasons I come to this meeting and hang out with you guys is to learn about the applications and what people are actually doing with AI. Because essentially my job is to make it faster, right? So I'll talk about a little about AMD and then some of the trends we see in AI and then how we connect that to the architecture and the performance optimization. Okay, so this is, actually what I want to talk about is AMD in Austin. So this is a picture of our location on Southwest Parkway. You can see the sun setting in the background there. This is actually, AMD has a huge presence in Austin. Everybody's probably heard of AMD. Anybody not heard of AMD? Actually, I should get people to raise your hands so I can make sure you can hear me. Everybody's heard of AMD, right? What you may not know is we actually do a lot of our AI development in Austin. So the software, which is the area that I work in, a lot of that software was created here. I brought some friends in the back of the room here, worked on some of that stuff with me. AMD, most of our employees are in Austin. This is our largest site. So worldwide, there's 28,000 employees. A bunch of revenue last year, a lot of growth in the company. AMD is a worldwide company around the globe. Where do we do our AI? So I actually work on the Instinct GPU, so that's what I'll be talking about. So the high-end stuff that goes into a data center, that's where I spend most of my time. AMD also does AI in our CPUs, right? There's special instructions that get added to accelerate AI in CPUs. It's in gaming chips, right? If you play a game, there's AI that's part of that. We build dedicated AI devices, and in a laptop, you can get AI accelerators that are part of that, and Windows has special features for AI as well. And then these are some of the companies that AMD works with. Part of the reason I mentioned this, I mentioned I do performance optimization. These are some of the guys that I work with. So I did some of the Copilot optimization stuff with Microsoft and ChatGPT with OpenAI and some of the meta workloads. So AMD, NVIDIA is not the only company that does AI. There's a lot of AI development that's done by AMD, and a lot of that's done in Austin. And the last thing I wanted to mention was ROCm. So this is our software stack. So ROCm was actually, that was created in Austin as well. So some of my early work was being part of the team that brought that up. And Greg in the back here was also one of the guys that worked on ROCm as well. So a lot of heritage of AI development right here in Austin.
There's a question in the back corner on your right.
Oh, yeah, sorry.
On your previous slide,
Yeah.
it looked like you had like the Huggy-based company out of Europe, and I'm just curious, like, would you work with different companies really closely in North America? What parts of the world are you?
There are a lot of AI companies in North America, but also, around the world. So a lot of companies in China, for example. We had a big business in China. Australia, we got supercomputers around the world. So yeah, the customer base is wherever the customers are. Maybe most of them are US based, but certainly not all of them. Strong European presence, a lot of European supercomputers use AMD, for example. Yeah.
Sorry to look it up real quick, but is ROCm CUDA for AMD?
Yeah, that's a good way to think about it. Yeah. I was trying to minimize the use of the art. No, but that's a good way to think of it. It's like our platform. I think CUDA means two things. There's a CUDA platform, which is kind of what this picture shows, the libraries and the compilers and the runtimes. There's also a CUDA programming language, CUDA C++. So we would call that HIP on our side. HIP is the programming language on our side. But that's a good way to think about it. Yeah.
Question.
Okay. Yeah. Question here. Sorry, what's our target market, or?
Yeah, maybe target market or main stakeholders and users groups that you're targeting.
Yeah, so most of AMD sales, actually, just looking at the size of the font on this slide, right? We sold a lot to hyperscalers, right? Because they buy a lot of volume. So a company like Microsoft might spend $1 billion on GPU, or even more, right? If you follow the annual report. So we did sell a lot to the large companies here, but we've also got smaller engagements with smaller companies, and those have kind of a different profile. The larger companies have more sophisticated engineering teams. The smaller ones require often a little bit more customization to make those successful. It's good. Yeah.
Do you guys manufacture a lot of your GPUs like at TSMC or in China or?
TSMC.
TSMC, okay.
Yeah. Good questions. Okay. So that's what I was going to talk about on AMD, I believe. And then what I wanted to do was talk about like these trends that I mentioned. And so I'll kind of connect this to like architecture things. So this is like my world, understand where the workloads are headed. And then as a result, what kind of changes do we need to make in the hardware and the software to make them run fast on top of AMD? So the first one I wanted to talk about was the reasoning models. I'm sure everybody's familiar with the thinking tokens and reasoning models. Does anybody remember when these came out? I had to Google it. It was about a year ago. It was almost exactly a year ago when OpenAI introduced O1, which was kind of this innovative technology. What they do is they would generate additional thinking tokens. So if you've used a modern model, I'm sure you've seen these. Some of the models, like DeepSeek, actually show you the thinking tokens, so you can see what the model is doing. In some cases, it's hidden. But the point is the model is doing additional processing to come up with a better answer, right? And we used to do this by hand. If you think about prompt engineering that you would do a couple years ago, actually, I think I did it at one of these sessions, I don't know, 2 or 3 years ago or something. It was like, the guidance was, in order to get a better answer, you had to kind of step the model through the process. Like, 1, 2, 3, 4, think about this, break it down, show me the steps, and then give a second answer.
Chain of thought. Yeah. Chain of thought.
The chain of thought, exactly. Yeah, that's the idea. So a couple implications then, right? So on the training side, how is this done? basically they did this process as part of the training, they automated it, and the response length would naturally grow with the encouragement of the prompting. There's a couple of techniques that used to automate that, the extensive RL with the verifiable rewards. If you could give it a problem where the answer is verifiable, like coding, for example, where you can check it, then that's very advantageous because you can automate the process, right? And that's what allows you to really scale. From a performance implication, like my job, like what does that mean? It's kind of the same. I mean, it's pre-training. These models looks pretty similar to what it did before. The biggest difference is on the inference side. So on the inference side, now you're generating the chain of thought or these thinking tokens. And so there's just a lot more token generation. So it changes the balance of what we need to optimize for. When you're doing inference, there's basically two phases, right? There's a pre-fill phase where you're processing the query, like if you're doing chat. That's a very flop-intensive, compute-heavy operation. And then there's the token generation part, and the token generation tends to be very bandwidth intensive. So what this does is kind of shift that balance where it's more token generation, which means you need more bandwidth, more memory capacity in order to handle that kind of a workload. So yeah, some of the computations we did, we would see maybe 10x more compute, so that, or 10x more tokens, I mean. So that's gonna put a lot more pressure on the KV cache and on the decode time. Conversely, I didn't really talk about that. I think I cut out some of the material here. One of the DeepSeek also came out about a year ago. It was right around Christmas of last year. It kind of ruined my Christmas, actually. But but one of the innovations in DeepSeek was something called MLA, which is multi-head latent attention. So they compress the size of the KV cache by pushing it into a latent space. You were talking about compression in the last talk too. So we've got two competing factors here, right? One makes it 10x bigger, the other makes it 10x smaller. The impact there tended to be more memory capacity on balance. I think we saw actually more than 10x the tokens. Maybe it was more like 20x. And then these models are bigger. So I think before DeepSeek came out, I got to think back. I think Llama 405 billion was maybe one of the largest mainstream models. So the model was bigger. And this was one of the first open source MOEs, which is of course the state of the art now. So that has some different characteristics. Specifically, takes a lot of memory capacity, but the compute is somewhat constrained. So again, it puts more pressure on your memory capacity. So I'm kind of saying memory capacity. I'm sort of stealing my thunder here, but we're going to talk about the value of memory capacity. So I'm trying to motivate some of the use cases for why that's important. And then some of the other things that impacted us. So the collective pattern was different. So there's more all-to-all. Previous models maybe had more all-reduced style patterns, and the memory capacity continues to be important. Any questions? Okay. Okay, so let's talk about another trend, right? So we just talked about reasoning models. So multi-modality, a hard word to say. We're just talking about, beyond text, right? So things like images, audio, video. The Sora 2 stuff that's come out recently is pretty amazing. So this is a slightly older slide, but there's a whole lot of models now. Almost every model basically supports video and image generation in addition to text. Typically, the way these work is you take the video or the text, you translate that to tokens. So the underlying model then is pretty much a standard transformer. So there's not like a lot of model innovation here, but there is a longer sequence length. There's more tokens, right? Because video is just bigger than text. So when you do this tokenization, you're just going to end up with a larger input. So the sequence length is larger. Does put some increased requirements on the storage and the I/O bandwidth. So as a computer architect, we have to make sure that the system's capable of delivering those. And then some of the video, it does convolutions. So convolutions were pretty trendy back when we were searching for cats 10 years ago or so. And then it kind of fell out of favor when we were doing LLMs because it was all text-based, it was all just gems. So now convolutions are back. Video codec support is important, so we can decode the video and feed that into the language model. Okay, and then long context support. So one example, we see multiple factors that are pushing up on the maximum context length that people want to run on these models. And I mentioned a couple of them already. So one is the video input makes the sequence length longer. People want to do summarization. We have these RAG systems where you pull a bunch of content off the internet and then you feed that into your large language model. we also have the chain of thought reasoning, right? So as you're generating all these tokens, as the model is thinking about the answer it's going to give you, that increases the sequence length, right? And so there's this pressure to push up the sequence length. I can barely see the picture, but what it's showing is if you go back in time, like if you remember BERT, for example, it was like 512 tokens or something, right? We thought that was awesome. Now we're talking, 1,000 times bigger. We're talking 1 million tokens or so. And so this puts a lot of pressure in a couple areas. One is the, one is the attention algorithm itself. So the attention is, grows with the square, the computation time of the attention grows with the square of the sequence length. So if you go to 1 million, all of a sudden, it's kind of the only thing that matters when you're running the model, right? It's all about attention. So you're seeing both from AMD as well as the other guy, like specialized instructions to accelerate the attention, specifically the softmax part of that, so you can overlap that and make that run faster. And then you're also seeing algorithmic innovation or software innovation. So people are doing things like sparse attention in order to reduce that complexity. It's not clear if those work yet, so from a hardware point of view, we're going to make sure that the slow old way continues to work fast and not necessarily bet on the software stuff going, but we're also working on evaluating and innovating on the software side. The other thing that the long context length does is it puts a lot of pressure on the memory capacity again, because you've got to store this stuff, right? And specifically in your KV cache. And so the picture here shows the size of the KV cache. I think we were looking, if we just look at the one that I highlighted, right? A 405 billion parameter model, if you have a context length of 128K, which is not uncommon for some of these use cases, like if you're doing video or even just a whole lot of thinking tokens, it takes 120 gigabytes of memory, right? And so I think at the time I put this slide together, we had a GPU that had 192 gigabytes of memory. The other guys was smaller than that. So, it's like your KV cache doesn't fit in a single GPU anymore, right? So it just puts a whole bunch of pressure on on the memory stuff. Okay. Question?
Yeah, so does AMD have something like the BF16 format, or is that just unique to NVIDIA?
Yeah, so BF16, everybody's got BF16 now, right? So Google created that with the TPU. I can't remember when. We've got FP8, we've got FP4, and there's a 6-bit format, if you can figure out how to use that. See those people shaking their head? Turns out it's not a power of 2. But yeah, it's kind of, so there's a whole lot of innovation in data formats.
So is this based on like FP32 stored in the model, or are we talking about that?
No, this is relatively modern. I guess I didn't put it on here, and I can't remember. It's at least B-float. It's probably B-float 16. Yeah, it's certainly not F32.
On the right.
Yeah. Yeah.
Now, in this, is the decoding of, say, JPEG, MP3, video codecs, is that all baked into the weights of the model, or is there a decoding step that happens first so that the raw pixels, waves, video pixels are passed into the model?
Right, so typically it's decoded first, and then you do some kind of tokenization to turn it into something that the model can process. Yeah.
Do you see it at a point where the context pressure is going to increase? I mean, GPT-5 actually has a smaller context size than the 4 models.
Right.
Right. Some of that is because you have larger chain of thoughts and all those things you mentioned earlier. But do you see, like, have you gone over peak context?
I'm not sure. Yeah, I'm not sure we're there yet. I mean, it seems like there's just so much value, right, in having those bigger contexts, because the models just become more capable if you're able to process those. I mean, I think we will see some use cases or edge cases where they don't need all that power, and there's a strong motivation to shrink and fit the model in some kind of a limited compute or memory form factor. So we may see a bit of a divergence, but I think there's just tremendous value in continuing to push it up. Yeah.
I had just read about, I think they're called linear attention models today, and on your point about cache sizes or KV cache sizes, there's a model that was just released called Kimi Linear, and those, it says a 75% reduction in the KV cache requirements for something. So I mean, that seems like it'd be a huge
Yeah.
difference.
there's a lot of ideas, and I mentioned the MLA that was part of DeepSeek. So they all have trade-offs, right? They're all, because people want the big size because it has value, and then you compress it, you lose some of that value. So the trick, it's like any compression scheme, right? You want to retain most of the signal, but still get the smaller stuff. It feels like there should be something there. I mean, it's n squared in terms of the computation. Can't I do, pretty well with something that's n log n or something that's close? So like I said, we kind of track it, but it does seem like there's still, a lot of people are still using just full attention, n squared, where they look at every element against every other element. Okay, good questions. Okay, so I've kind of teased at this about, memory capacity, and I called it underappreciated. And the reason I use that word is if you compare memory capacity to something like flops or bandwidth, it's a little bit easier to evaluate the value prop of those things. Like if I turn up the flops and I'm trying to compare two processors, like previous generation AMD to next generation AMD, I could run the same benchmark or the same matrix multiply size, and it would get 2x faster or something like that. I could measure that. And the same is true for memory bandwidth, right? If you just run the exact same workload and you see the value there. Capacity is a little bit squishier, right? Because if you run a model like let's say Llama 8 billion and it fits in your previous generation memory and you put more memory on, it doesn't change, right? Because you don't need the memory anyway. And so what you need is something that doesn't fit in the previous one. How do you measure the previous one then? So it's a little bit squishy. So the trick is, in order to evaluate, you actually need to change the workload. The simplest thing you can change is the batch size in the workload. So basically the same workload, if you increase the batch size, it takes more memory capacity, and there's some ways that change can increase the performance. Larger batch size, typically leads to like larger gems, which tend to be more efficient on a GPU. So you can do those kind of evaluations, but squishier is the word I use because how do you choose the batch size? What are you comparing? So sometimes the capacity is just not as directly compared, I guess. So we'll talk about, so some workloads, they see no gain, like if it already fits. In some cases, you can see these spectacular multi-X factors. Which one do you believe? Can you believe your GPU vendor? Can you believe AMD? Perhaps, maybe not. Depends what we're trying to sell you. It is expensive. So like 30% of the GPU cost is actually the HBM memory, the high bandwidth memory that we attach to it. So this is actually a question we ask ourselves a lot is like, how are we going to get people to pay for this stuff if it's, what's the value proposition of the memory? So what I want to do is go through a couple examples of where capacity does deliver value. So we'll talk about batch scaling, and we'll talk about some cases you can fit the whole model in a single GPU. That has some advantages. And then we'll talk about the KV cache management and how that can be improved with more memory capacity. So I've got 3 slides here that all kind of follow the same pattern. So let me introduce this picture. So imagine that you're ChatGPT. So like ChatGPT, the inference server. And so your job is to get a whole bunch of incoming chat requests, and you have to return a response in like a reasonable amount of time. So the primary parameter that you can choose to optimize that is the batch. Like how many chat requests do I accumulate before I respond, right? And if you do 1, that would provide the minimum latency, because you're not waiting for anybody else to kind of gang them all together. However, if you do 1 request at a time, your efficiency or your use of the hardware would be pretty terrible. So your throughput would be pretty bad. If I wait for 500 or 1,000 requests, then I can put them all together. That allows me to use the hardware more efficiently because you don't have all these kind of edge conditions. So I mean, if your inference server was a highway, the first case where you're just waiting for 1 would be like a presidential motorcade, where you shut the whole thing down, 1 guy, there's nothing else on the road. But the efficiency of the use of the highway would be terrible. Whereas the second case where you're batching everything together is kind of like a bus, where you get everybody together and high utilization of the lanes. So we'll look at a couple of these pictures and I'll talk through the examples. Now both of those are actually interesting. So the first one, like online inferencing, that's when you're trying to respond as quickly as possible. That's valid when that's what you need to do. The offline inferencing, if you're doing something overnight, well then you can accumulate 1,000 requests. That's often used in training or fine tuning or in cases where latency is not critical. So it's not like one's better than the other. Yes?
So one of the concepts that we've been
You just go, right.
But either do that or if 10 requests come in flush.
Mhm.
Is there anything like that? Because microbatching can give you both time bounds and efficiency bounds.
Right, right.
Is there anything on those ends?
Yeah, people do absolutely do things like that, right? Because yeah, it's ultimately the more you can batch but still hit the latency requirement is a good thing. So yeah, micro batching like that would be absolutely part of the solution.
Is there any microbatching happening like as part of the hardware layer?
Not at the hardware level. No, that would all be at the software level making those decisions. Yeah. Yeah.
Here, in the case, for instance, when I'm working with my coding agent, it's doing online inferencing, but if it takes 5 minutes or 10,
Yeah.
it's not that important. So it's online inferencing where latency is not a constraint. So this switch of doing these two kind of the batching side,
Yeah.
it's something that just simple is like variables, or it's a boolean that true or false, or it needs more complicated orchestration, because in this case, here you're just picking two scenarios, but it could be 3 or 4. So how easy it is to switch between one and the other?
Yeah, it's pretty easy to switch, right? I mean, you can, like you were saying with the micro batch, you can just accumulate a larger batch. It's not like a fundamental change in the hardware of the software. The batch size is very dynamic, and a lot of applications they'll change it, right? I mean, you mentioned one case. You could have a heuristic where you accumulate for a while and then launch stuff. You could, it's almost the same software, right? It just changes how you use it, like the size of the operations that are put through. The gems get bigger, the communication gets bigger. So if you accumulate more, even on top of the same software system, you'll be more efficient. If you kind of go quickly, then it'll be less efficient, but you'll provide better latency. Okay, good questions. Let's see, is there anything else I wanted to say here? I guess the online inference tends to be more bandwidth constrained because you're generating smaller problems, which makes it harder to use the compute efficiently, which means there's not enough reuse to get efficient compute, so it tends to be more bandwidth constrained. Whereas on the right-hand side, you're getting larger operations, larger gems. That means you can use the flops more efficiently. So the point is, left is kind of bandwidth sensitive. The right side is more kind of flop constrained. Both important.
I think this is a good moment to just elaborate on the difference between latency and throughput. Because people like to get those mixed up a lot. So people are like, oh, the internet's so slow, the bandwidth is too low. It's like, okay. So I liked your motorcade example a ton. So latency is just how long it takes for you to get something back, right? It's not telling you how much you're going to get back. You're just getting something back. Throughput is how much you can process within some amount of time. So another good example, along with the motorcade, is like a motorcycle has low latency, which is good, but it has really low throughput. Like you can only carry 2 people at most, at least in the U.S. Those who get it. Anyways, but if you have an 18-wheeler, it's going to be way higher in latency, right? That's bad. It's going to take a longer time to get the truck rolling and get up to speed and moving. It's also going to be a lot longer to slow down, but it can carry so much stuff at once, or you could cram so much, equipment or goods or people in a large truck. And so those tend to be inversely correlated in the physical world, and it's in the digital world that people like to imagine they're both the same thing and they both go up. Yeah.
Thank you. Yeah.
Memory stuff about if you had higher memory capacity, what would that curve look like? Would it just shift up?
Yeah. My next one. No, great. Did you have a question on the last slide? Maybe we'll have to go back.
If you increase memory capacity, wouldn't it just increase, like you could do batch size of 512? How would it increase upward?
Yeah, so let me talk through this slide. So it's possible that typically the way this works is you're given a latency constraint. Like I have to respond within, what are my units, like 1,000? I have to respond within 1,500 seconds, say, or milliseconds. So, and that sets your batch. Then you would turn on the batch until you're able to hit that constraint. It's possible that you don't have enough memory capacity to run at the optimal batch size. Does that make sense? Like I'd like to run at batch 32, for example, but when I increase the batch, it increases the memory usage of the model, and I may not have enough memory capacity. So that's one area where higher memory capacity allows you to push the batch up, still meet the latency constraint. So it can kind of unlock this batch scaling, and it's a pretty significant performance factor, because if you're on the left-hand side of this curve, you're at a very inefficient region. If I could just increase the batch a little bit, then I could get significantly higher efficiency. I mean, the point I chose here was like a 16x increase in efficiency, which could be unlocked if I have enough memory capacity. These MOEs that are so trendy that everybody's running now, they kind of tend to fall into that pattern because they reduce the computation with the sparsity, but they still have very high memory capacity. Like if you ran the old Llama 405, it's a dense model, so it's got 405 billion parameters and it does 405 billion, parameters of computation. Whereas a sparse model like an MOE like DeepSeek, it's 670 the size of it, but it only does 37 billion computation because it's sparse, right? So it tends to fall into this area where it needs more memory capacity.
So do you see then with MOE models that you would have like more of a curve up versus like this one kind of flattens out quicker?
No, they tend to flatten out because what happens is as you increase the batch, you get more and more reuse inside your GPU, from the stuff that I work on. And so as you get more reuse, then you no longer become memory bandwidth constrained. There's a different bottleneck. You become flop constrained essentially. So it transitions. So they all kind of do this kind of curve. Okay. Let's see, did we do this slide? Yeah, so the capacity enables a higher batch size. Spectacular, I use the word spectacular, if you're on the left side of the chart. Yeah, intuitively, so the reason that increase in the batch helps you so much is you have to read the weights once from memory. And if you have a larger batch, like multiple samples, you just reuse those weights without having to go fetch them again. So it's almost free, like it almost goes up straight. There's various reasons it doesn't go completely up straight, but it is a very, very steep curve if you can read them once and use them multiple times. I can't read, what's my last point there? Oh, yeah, latency constrained inference. So that's one area where capacity could really, really help you to get some really spectacular performance gains. Any questions? We're never coming back to this slide. Yeah.
Why don't the service providers just have that one GPU or cluster of GPUs always run the same model so that you can get infinite batch size and you're just putting them in there without having to reload the weights? Why would they be reloading the weights on every batch?
Yeah, so the weights, they're typically stored in HBM. So when I say reload, I mean load them from the HBM to the smaller levels of memory hierarchy on the chip, like the registers or the caches, and those aren't big enough to hold it. So so they get evicted, and then you read them back again. It's typically, you don't want to store it in the SRAM of all, a whole bunch of GPUs, because you'd have so many that the communication cost would kill you.
Okay. So the chips nowadays do not have enough cache space to hold all.
That's always been true. Yeah.
There are people that are doing those kind of things, but it's pretty big, right? I mean, like DeepSeek in FP8 is 600 gigabytes. That's bigger than the HBM memory on like the GPUs that we ship today. So it's way bigger than the SRAM that's inside the GPU.
How big is the cache size on this chip?
I'd have to, I don't know. Probably lose a zero. Ask me
Probably
afterwards.
probably in the megabytes or tens of megabytes.
Megabytes, yeah.
256, okay.
Yeah, that sounds about right too. Yeah, something like that.
Yeah, and if anyone's curious, they can look up the relative differences in timing comparisons between memory hierarchy levels. It's like 1 second at the cache level is like some number of years, in the storage level, so.
Yeah. Okay, so let's do another case here. So same chart, but now we're looking at a different use case. So in a different region of the chart, actually, right? So now we're in the throughput regime. And if you have enough memory, you could actually fit the entire model in a single GPU. So what we're showing here is that the case? Yeah. So so this is MI300, which is the GPU we shipped about a year ago. It has 192 gigabytes of memory. Llama 70 billion, it was kind of a trendy model back at the time that this GPU was available. And in 192 gigs, you could fit it. You could even fit it in bfloat 16, certainly in FP8. with enough room for a KV cache and other stuff. So the advantage there, what the chart is showing is actually two different ways to parallelize the model. So the one on the bottom, we use something called tensor parallel 8, which means we're using 8 GPUs. They're each running 1/8 of the GPU, and it's basically optimized for latency. So you can see on the left-hand side of the chart, the latency is pretty good with that TP8 config. In fact, it gives you better latency that you can get with any of the configs on the purple one. What we're doing on the purple one, we still have 8 GPUs, but each one of them is now running a copy of the Llama 8 billion. So what that means is the bottom one's good because we're applying 8 GPUs to the same problem, whereas the top one is good because we fit the model in a single GPU, and therefore there's no communication cost. The bottom one has a whole bunch of communication costs that actually you spend about half the time on the communication. So I don't know if I explained that well, but the point is it's a trade-off, right? And if you can fit the model, you can eliminate all the communication costs. It also simplifies the programming model because you don't have to think about how to parallelize across the different GPUs that you're targeting. How much time do I have? Couple minutes, okay.
If you are doing tensor parallelism, you're sharding the model across GPUs, right?
Yeah.
Are you able to increase your overall batch size as a result of that? Because instead of having like full copies on each, you just have more memory, right?
Yeah, you'd have a chunk of the smaller chunk of the model on a GPU, so you would have more memory per GPU. But typically, when you're doing tensor parallel, you're trying to hit a low latency target, which means you can't increase the batch size and still hit that latency target. Okay. And I got one more. So the case here, this is around KV cache management. And so how many people use VLM? Or the VLM, okay. See a few hands up. Yeah, so VLM, it has a heuristic where if it runs out of KV cache space, it actually preempts things out of the KV cache, and then you recompute them. So that's actually the opposite of what the KV cache is intended for. It's supposed to store all this information. But that's what happens when you run out of memory. So what was the case here? I think we were using, this is Llama 4 or 5 billion, and we ran it on a GPU that had 640 gigabytes of total memory. So on the surface, it seems like that would fit because 405 is less than 640. However, you have to have memory for more than just the weights of the model. You also need to store the KV cache. And so you don't have room for the KV cache, it gets evicted, it generates this horrible, scary message. And so if you have memory capacity, you could avoid those evictions and you can get close to a 2x performance gain in this case. So there's a whole bunch of advantages to the capacity. Longer context, it gives you backtracking for the reasoning. You can run more concurrent sessions, which is another way to use the KV cache. Okay, I have about 2 more slides. Question?
I did, but it was 2 slides ago.
Okay.
Pipeline parallelism. I've seen that technique
Mm-hmm.
used when training. I haven't. Is that something that you can use for inference that would help, or is it just you get way more latency? Or
you can use it for inference. You can't use it for low latency inference because you hit it on the head. Yeah, it's a throughput optimization. So yeah, it would fit on the right-hand side of my chart that I'm showing you. That could be one of the parallelization techniques you could use.
And it doesn't, but does it help with GPU saturation during inferencing, or I guess if you were capacity constrained, would it help with total throughput?
It is a good optimization if you're capacity constrained because you could add additional GPUs, which gives each GPU comes with its own capacity, and it has fairly light communication cost. So it is a way to, effectively add capacity at the cost of another GPU.
At the cost of another GPU, right?
Yeah.
But you'd only use it in a multi-node setting.
Sorry?
You'd only use it in a multi-node setting, right? Like if you need to go from one node to another node, if you're just within one GPU or within one cluster, you want to use pipeline parallelism.
Yeah.
Really? Okay.
And if you do tensor parallelism multi-node, the communication overhead is too low, so it's actually a lot worse your throughput.
Well, if I'm doing, let's say, pipeline parallelism, I'm sharding the model, instead of, like say in the top example, I have a full copy of the model on say 8 GPUs, right? Say, we're doing FP8, so that'd be 70 gigs roughly. If I were to then use data parallelism or pipeline parallelism, shard the model into 8 pieces, make it 10 gigabytes with 10 billion parameters, should make the math simple. You have more capacity per you have more memory capacity per GPU, you can increase the batch size, right? Or no?
Yeah, but the overhead from decommunication is just going to outweigh any benefits you get there.
We'll take this one offline. We can duke it out afterwards. All right, let's do my last 2 slides. So my point here, yeah, so there's a lot of factors that go into the performance, right? So, we all focus on flops and HBM bandwidth and the communication bandwidth and the capacity. Some other things in addition, so the vector performance. So I mentioned softmax before. There's other operations out there that are computationally important that are not matrix multiplies. And so it's really important that you provide enough horsepower to handle those as well. So one example is the softmax. There's a lot of format conversion that goes on. So people are innovating. We did bfloat 16, now people are coming up with custom 4-bit formats that do this or that. And so when you read the data in, you actually have to do some processing to turn it into something you can feed into your matrix multiply. That takes some vector computation capability. Not everything's a gem, so a lot of the ranking or recommendation models, the things that are not LLMs, have a lot of element-wise operators, that are doing. So it's important that you have a balanced machine that can handle those as well. Transcendentals are really important for attention operations. Latency is really important. So we've been working on the flops and the bandwidth. So what's happening is that the inner parts of the computation are getting really, really fast, which means that the time in between is becoming increasingly important. So GPUs tend to break things up into these kernels, we call them. So you spin up the kernel, you get started, you do some computation, and then you run another kernel. The time between those kernels is becoming important. So it's maybe 1 to 3 microseconds on a modern GPU. Some of the kernels that I'm seeing are like less than 5 microseconds, so you can sort of see the problem there. So really, really important that we optimize the latency. And then it's not just about the GPU, so the CPUs are important too. A lot of machine learning is done with Python code. Python code is not very fast. And so being able to do stuff to optimize that, either get the Python out of the critical path or compile the Python or store graphs that you can replay without having to go back to the Python. Those are all really, really important for performance. And then there's also things that aren't run on the GPU, so the RAG, the pre-processing. So it's important to have a balanced system that has both a fast CPU as well as a fast GPU.
What does GEM stand for?
Which one?
GEM.
GEM.
General matrix multiplication.
Yeah, it's my favorite word. Sorry, I didn't even put it on the slide. Yeah, it's a matrix multiplication. It's a kind of a silly acronym, but yeah, it's a general matrix multiplication from like years and years. Does what?
Attention.
It does. Yeah. It does. Yeah. It has matrix multiply combined with the softmax operation and vector stuff. So it's kind of a fancy matrix multiply, basically.
Great.
Okay. Last slide. So what are we doing? If you summarize it, right? So clearly we're going to keep pushing up the speeds and the feeds at AMD. So that's all the flops, bandwidth, and the scale up and the scale out, all that stuff. Optimizing the latency, right? I mentioned, just the back-to-back stuff matters more and more. Looking at more levels in the memory hierarchy. Power's going up in the GPUs. A couple years ago, we shipped 500 watt GPUs. Now we're shipping 1400 watt GPUs. Somewhat counterintuitively, that's actually a good way to improve the performance per watt at the cluster level and the TCO of the system. ROCm, right? So I mentioned ROCm a little bit, invented right here in Austin, Texas. If I look back, we did a whole bunch of LLM inference last year. A lot of our new opportunities are in training, so that's all going on now. I think the most important thing, though, for as I look at what do I need to do in my job is flexibility. That makes sense. That's been a lot of the reason that GPUs have been successful is because they can react to these new problems. If you look back, we were doing, like I said, convolutions and cats not that long ago. Now we're doing LLMs. The LLMs have a ton of diversity in all these papers. People are pushing the hardware and the software in different ways. So having a system that's got the balance and the flexibility to be able to respond to those is probably our most important design criteria. So with that, I will stop. Thank you for your time.
Please give him a round of applause. I'm going to cut the recording off, but just stay seated for a moment.